Hi everyone, today I'm going to present a topic on enhancing fundamental energy limits of field coupled nanocomputing circuits. Going to intro, future generated systems face major challenge with energy dissipation, so this cannot be resolved by current technologies. There is an urgent need for strategies that operate near the fundamental energy limits of computation, ensuring efficient energy use and preventing data loss. New innovative approach is that leverages reversible circuits and recycling of bits, aiming to reduce the fundamental energy limits of field-coupled nanocomputing circuits. Simulations on advanced benchmarks shows that our method can reduce energy limits by up to 51% without impacting system delay and making the first successful post-synthesis application by using these strategies in FCM circuit designs. Here we learn two techniques. One is the quantum dot cellular automata and the other one is the reversible computing technique. In quantum dot cellular automata, it is a nanotechnology that serves as an innovative alternative to conventional CMOS technologies used in electronics. Each QCS cell consists of 4 quantum dots arranged in a square pattern. These dots trap electric charges, allowing free electrons to move among them. These electrons are subject to Coulomb forces, causing them to repel each other and settle at opposite corners of a square, establishing stable polarization states that represent binary 0 and 1 as illustrated in this image. The proximity of one QCS cell to another affects their polarization through Coulomb's interactions, a principle that can be used to create logic gates. And other is the reversible computing technique. Reversible computing technique involved designing systems that can revert to any previous state without losing information. Modifying a circuit to be reversible often requires changes that could impact timing and space within the circuit. To balance these trade-offs, a formal method to quantify energy loss due to irreversible logic operations is based on Landau's principle. Landau's principle states that the ensure of information in a computing process results in a minimum amount of energy dissipated as heat. So here there are different types of quantum dot cellular automata and gates like conventional 1-bit recycling and fully reversible types. In this scenario, where the input match the output, energy dissipation is minimized, demonstrating a practical application of these theoretical principles. However, this method increases circuit complexity due to the need of additional components to maintain reversibility. So in this image, there are three different versions of an AND gate and how each manages energy recycling of inputs. First one is the conventional AND gate. Conventional, this is the standard representation of a AND gate where two inputs X and Y produces an output X and Y. The output is true only if both X and Y are true. This diagram shows the basic functions without any energy recycling features. AND gate recycling energy of one input in diagram B. In this version, the AND gate not only performs the logical operation but also recycles the energy of one input. It is shown that the energy from input X is being recycled, potentially reducing energy waste. The output and the operation remain the same as the conventional AND gate, but with added and efficient energy for one of the inputs, that is fully reversible AND gate recycling energy of both inputs. We can see in diagram C. This diagram represents a fully reversible AND gate that recycles the energy of both inputs X and Y. This design is the most energy efficient among the three, and it reuses the energy from both inputs. It performs the same AND gate operation, but it is designed to minimize energy dissipation fully. This diagram illustrate progressive enhancements in energy efficiency for logic gates, moving from conventional design to more advanced energy conscious configuration. So here application of proposed method for half-adder circuit. This image has different types of configurations of a half-adder circuit, each designed to variations in handling fan-outs and delays. First one is the conventional half-adder. This diagram represents a standard half-adder used in digital circuits to perform the addition of two binary digits. It consists of two inputs labeled A and B and produces two outputs, the sum, that is S, and carry out C out. The sum is generated by an XOR gate denoted by gate 1 and 4, and the carry out by an AND gate, gate 5. This basic design is straightforward but does not feature any optimization for energy efficiency or delay. Half-adder exploiting fanouts without regarding delay, that is the second diagram. This configuration modifies the conventional half-adder by optimizing the layout to exploit fanouts without increasing the signal delay. It maintains the functionality of computing the sum and carry out, but rearranges the gate and connections to optimize signal paths and reduces the potential for delay introduced by gate loading. It aims to increase efficiency while maintaining speed. Next is the half-adder exploiting fanout with delay penalty. This third diagram depicts a half-adder that also exploits fanouts but at the cost of increased delay. This design may introduce longer paths or additional gates that handle the increased complexity and manage the signal integrity, which can down the operation. So this shows the same basic like half addition. This can be achieved with different trade-offs in a circuit design. Next is the algorithm for reducing fundamental energy limits. The main idea of our method is the summation of the upper loss for each gate in the design, the maximum entropy that a gate can receive. We are overestimating the losses and underestimating the gains since we are not considering conditional reversible cases. We consider that this is the fair trade since we are now solving a polynomial problem instead of an exponential one, and this enables the evolution of larger circuits. Here in this image, the operation of algorithm is designed to build chain of n bits recycling bits whenever possible. It has two key phases. Algorithm 1 is the building chains of n bits recycling gate, and this algorithm starts with a list of circuit nodes, that is the netlist, and process them by their ranks, which likely represents some metrics like energy efficiency or computational priority. It chooses children for each node, builds a chain of these nodes, and updates the chain until it meets certain criteria like a specified length or efficiency threshold. Visual representation in two. Here there are two parts. One is the generation of chains of 1-bit recycling gates. This section shows the step-by-step building of chains from a starting point, that is the rank 0, through various iterations connecting nodes A, B, C, D, and so on. The lines represent the linking of these nodes to form a chain that recycles 1 bit aimed at reducing energy dissipation. Next is the part B, integration of fully reversible gates. It is a similar step-by-step process but focus on integrating fully reversible gates into the circuits. The start point shows node N and it progresses the connecting are adjusted, indicated by red lines, to enhance the reversibility, thus improving the circuit's overall efficiency and reducing energy losses. This diagram beneath the algorithm steps to visualize the changes in the circuit structure over iterations, demonstrating how the algorithm optimizes the circuit by rearranging or altering connections between the gates to achieve the desired n-bit cycling circuits. Next is the benchmark results. Here there were different types of benchmark results and the delay and also different types of energies. Here delay is given in number of stages and energy means the approximation of fundamental energy limit calculated with the proposed method. Next, examination of simulation results from top-tier benchmarks demonstrating the effectiveness of our approach. The results of these benchmarks are presented in a table that detail the size and original energy dissipation of each circuit. Along the side, the energy savings achieved through our approach. This original delay of each circuit is maintained, showing that our method does not adversely affect performance. Significant reductions in fundamental energy limits were observed with an average decrease by up to 25% and on average by 17% without any delay penalty. So here simulation results shows that if this approach was fully applied, it could potentially reduce energy consumption by up to 80% and an average of 51% across different benchmarks. However, in this case, where our method could not utilize fanouts effectively, we achieved a reduction of energy consumption by 50% for specific circuits. So in conclusion, this is a straightforward yet effective approach to reduce energy dissipation in nanocomputing architectures using partially reverse gates, which while computationally intensive proves highly effective in large scale designs. This technique allows for significant reductions in energy usage without compromising the delay, enhancing overall circuit efficiency. Thank you.